Okay, well, hi everybody. My name's Steve Purves. I'm primarily a software engineer, but I've got a background in signal and image processing, originally electronic engineering. And I spent a lot of time in oil and gas, working with geoscientists, processing geophysical data and 3D seismic surveys. So a lot of the analysis there is statistical, stochastic, conversion, classification problems, image and signal processing, lots of feature extraction. But for the last 5 years, I've been working more in cloud and designing back-end and front-end web-based software with lots of visualizations in. And particularly, I've been working quite a lot with graph data sets. At the minute, I work from a US-based consultancy who do a whole bunch of things, but what a lot of our guys do is to do with graph data. So we do a lot of work setting up graph databases for people, helping them load data into graph databases, and then putting together front-end tools to help them spend a lot of time interrogating, slicing, and walking through these graph data sets. So what we've been working on more recently is how the world of graph and graph analytics, because when you're dealing with graphs, you have a completely independent sort of ecosystem of measurements that you can make based on graph theory, how that intersects with machine learning. And it's an incredibly interesting area. The intersection is huge, but it's actually, what I found, it's a little bit hidden. So it's actually sometimes difficult to get at where the graph is in machine learning and vice versa. Sometimes you'll find papers that look like nothing to do with graph, but they've actually used a very clever application of a graph algorithm in the middle of it. And vice versa, some graph analytics algorithms are actually quite intractable, and we need to find approximations for that. And machine learning starts to step in there to give a different and viable way to do to carry out algorithms on graphs in a more reasonable time computation-wise. So this talk is trying to simplify and summarize 3 of the most interesting areas that I found in this intersection. All the links to all the papers we've looked at and the techniques we've been reviewing are up on GitHub. So anything on here and more is available online. Oh. Okay. So the talk, I'm going to assume nobody knows anything about graphs and a little bit about machine learning. So I'm going to do some very basic stuff on graphs to try and explain what they are. A little bit about machine learning basics, because I want to implant a couple of ideas before I walk through, hopefully, an escalation of how to use graph at different levels in machine learning. And this isn't all based on work that I've done, it's based on where the literature is going and some of the most prominent bits of research that we've found. So what is a graph? So we're not talking about pie charts. We're talking about a mathematical abstraction. So in its purest form, it's a collection of, it's a set of vertices and edges, which we can organize in order to represent something. Vertexes or nodes represent the entities within the graph, and the edges can represent a relationship of some type. Now, graphs and simple graphs like this, mathematical graphs, can be used to represent a huge array of different problems. So a very famous one by Euler was the 7 bridges of Königsberg, where he proved it was impossible to do a walk taking in all 7 bridges from all 7 land masses. And he proved that by completely abstracting it down to a graph representation. So that's a topological graph because it maps to some real structure. But it can be an organizational network. It can be a family tree. It can be something that doesn't have to have any sort of layout, any type of network in any shape or form you can use a graph to represent. And you can do things like find paths through them, etc. And again, you can use graphs to represent state transitions and temporal things. So graphs can march on through time. A good example of that is, imagine a game with player A and player B that have to swap positions on a cell. The actual graph of that game would map out all the possible positions of player A and player B, and by the time you've built the graph and found the shortest path, you've solved the problem. So they're incredibly powerful techniques. They've been used in image processing in computer vision for a long time, and you find them embedded in a lot of little bits of feature engineering in different papers as well. There's various types of them. You can have undirected, unweighted, which is the easiest to deal with. They can be directed, so edges can only point one way. They can be acyclic or cyclical and have loops. They can be colored, which is interesting because that means a vertex can have a property. They can be weighted, so the edges also could have a property of some type. And a reduced form of that is they could be signed, where edges can be positive or negative. So graph theory describes the behavior of these simple mathematical graphs, and there is a huge amount of algorithmic methods that we can apply. And graph analytics lets us find things like shortest paths. So examples like if you have a graph of a supply chain, you can find out the shortest routes between those two. You can cluster and find out how things are grouped in the graph. So you can take some property or some edge property. One example is if you take a group of MPs and you build the graph of which MPs voted with each other in each of the votes of Parliament, and label the edge with a frequency, you could actually cluster on the inverse of that and find out who tends to have the same views. Another thing is fraud there. In fraud analysis, clustering is used a lot because kingpins tend to be in between us, if you like. So another measure actually is centrality. In search, you can find out how important somebody is in the distribution. And like I say, for things like fraud, kingpins tend to be sparsely connected to larger groups who are further connected. So that's one sort of heuristic measure that is used often in fraud. So there's an entire separate branch of analytics to look at graphs, and some of these algorithms, actually finding them are extremely difficult. Similarity, for example, matching two graphs and finding out if two graphs are isomorphisms, if they are actually the same, is actually NP hard. So different problems, different approaches are used to approximate that. So what is a graph data set? So far we've looked at graphs, simple mathematical graphs. Graph data sets are actually what's called a multigraph, and this is, or a property graph. And this is where you have a multitude of different node types and vertex types. But they can be used to represent different things like transportation networks, where vertices would be cities and edges. Sorry, cities and stations, and edges would be roads or rails, or a social network, where vertices are people or businesses or clubs. And edges would be the different interactions between the members of that group. So these networks tend to be far more complex. But graphs like that are actually everywhere. So we find out a lot of data sets either inherently have some type of graph property with them, or we end up making our own. So a lot of time in data science, when people are working with graph data, you can splice together lots of disparate data sets and represent them in a graph, and then use technologies like graph databases to quickly access and do traversals across those and answer some class of questions very quickly. So they're actually highly available as well. So applications. There's a huge number of applications coming out from zooming in on a single person and analyzing their ego network. And this is a very important trick. A lot of the time, a full graph is too complex to comprehend. So you go in and you extract a subgraph around a particular node, and then start analyzing the properties of that one subgraph. And then you'll repeat that for various nodes in your network. And you can use that to do things like fraud detection, supply chain optimization. You can look for bottlenecks and hotspots. And you can do a whole bunch of analysis on that. So the concept of the ego network, or that subgraph, is very, very important. And one of the things that we find now is that why we're getting why we're moving into machine learning on this is that we find a lot of companies are actually just obsessed at the minute with visualization. And so they're asking for visualization systems to be built in order to manually slice and dice through those data. And it's not until they have a visualization system like that they start to realize this is a bit too much data to go through. But even though they still want the tools, and the next obvious layer of that is to start to bring in machine learning alongside the standard analytics to start to automate some of the questions and workflows. So quickly summarizing. So graph abstractions and algorithms can be used to solve problems, and we can impose graphs on any data that we might have, even if it's not naturally a graph. Definitely, if we've got data that is a graph, we should be exploiting it, because we have some rich relational data that we can pull out into our analysis. But in general, graph analytics, in order to use them on large data sets, we have to extract simpler graphs that graph theory can handle. So, machine learning recap. So, this is just to embed some quick concepts to make sure everybody's familiar. So, imagine supervised learning. You have a situation where you have a feature vector, and that's pushed through a supervised learning algorithm to make a decision between one or two classes, so a classification problem. So the point here is machine learning spaces work on vectors, not graphs traditionally. And in the process of gathering data and feature engineering, of course, we would build up potentially quite large feature vectors in order to represent our input space. So for example, in a disease risk assessment, we'd be bringing in data from lots of different sources, medical history, etc., pre-processing those into features to build these huge multi-dimensional feature vectors. And of course, that problem can get very large. Those feature vectors can become very big, and that increases the computational cost of training an algorithm. It becomes more difficult to train, and the sparsity that you get within these spaces, because generally massive feature vectors aren't, that feature space isn't densely populated with information. It's all squirreled away in subspaces and manifolds and little pockets. And that sparsity actually causes problems in training. So one step that we all know is typical is to do some dimensionality reduction on that. And that to create a smaller dimensional representation of the input information that still covers the majority of the information within the input space. And that's termed as an embedding. And here we have a simple picture of that, which might be done by something like PCA, principal component analysis, although there are far more sophisticated embedding algorithms. So, just another example of an embedding, a low-dimensional representation, is imagine we have a feature space, a two-dimensional feature space. So we have two features, and we have another number of points in our training set that's actually distributed around a curve. What may be more useful is for us to extract that lower dimensional embedding, which is the S line up the middle, to be able to actually analyze in one-dimensional space to start to see where groupings and clusters are. What's interesting about that embedding is it represents the majority of the variation in the input data. It's taking care of problems with the multiple values in one feature dimension, and it's also invariant. You can rotate the S. So we build invariance in at the same time as making the information more compact and more tractable. So I just want to keep an idea in our heads of that concept of an embedding. Okay. So there's actually much more than these three things in terms of the intersection of graphs and machine learning. But I've just picked out through three that I think are the most interesting. I think that build on each other. So I'm going to take us through that now. So let's concentrate on a particular problem, that of entity classification. So you could be doing fraud detection, risk analysis, or anything here where you're trying to assign a label to a particular entity within your graph. So we might have a graph like so, with various entities, and for example, they might be fake identities, for example, or fake Facebook accounts, or something. We would like to actually label them as real or fake. What we might do in entity classification without a graph is we'd have lots of training data sets, which would be information about those individual identities, and we would extract features. We extract information from that in order to build features. For example, the personal details, social security details. We might mine text associated with those accounts to find to pull out similar things from bios. We might actually use images from those accounts, but the key point here is we'd be limited to treating these things in isolation in order to build features to train a system. When we have a graph, we've naturally got this densely connected data structure that we can draw from. So immediately, yeah, we can bring features out based on the properties of individual nodes, but we can also do analysis on the graph in order to label and add additional information into nodes based on properties across the graph. So for example, you could run clustering and look for communities and label particular nodes as members of certain communities on the graph. You could look at the degree centrality, so how well connected anybody is, and the betweenness, which is the how well connected they are to densely connected groups. And all the sort of graph analytics algorithms that you can apply across the graph, you can use those to generate additional node-based features. And then the third level that you can take it to is you can start looking at individual nodes and pulling out subgraphs or ego networks and using those to span out and actually make measurements around the different subgraphs of each node. And that's another source of features that you can build into a feature vector. So what you can do is you can take per node information that you would be using traditionally, if you like, and then you can bring in this additional information that you can only get by considering your input data as a graph. The issue is, by doing this, because a lot of the graph analytics only work on simple graphs, we might have a graph like this. This is quite complex. We've got an identity that has an accessed edge to a certain IP address. This is contrived, obviously, but and who has an owns edge to a telephone number that called. So what tends to happen in practice is you need to do, for a given node, you need to make multiple subgraph extractions in order to make multiple measurements. So there's a huge amount of information in the graph, but it brings you back into the feature extraction and feature engineering conundrum, where you're balancing which information you're going to measure. So you can readily draw on more information across the graph, but you do need to put in more feature engineering effort to do it. You need to balance sort of which graph-based information, which vertex information you're going to be doing. There's additional computational costs because some of those analytics are not trivial, and there's lots of manual engineering and complexity. And when you take an approach like that, it's always, for every metric you select, you're leaving out information that might actually be important to your problem. So there are people doing this. There are papers out there about bringing in and building features using these analytics. They also, interestingly, I haven't covered it, they use it also to build cost functions that are directly related to the graph to help train systems. But wouldn't it be a better way? What if we could actually just suck in the entire essence of our graph without having to do that cherry picking about which measurements to make? And it turns out that, well, graphs are already vectors as well. So a graph, a simple graph like this, is actually fully represented by its adjacency matrix. So for any given graph, you can represent it by an adjacency matrix. This is a weighted undirected graph, and it's one of the simplest ones to analyze, but the adjacency matrix ends up being symmetric, and the weights are conveyed in each cell. And that fully describes the graph structure. This is a famous example. This is a co-occurrence matrix, or an adjacency matrix, basically, for a famous, The Miserables, my French accent's bad, I'm not going to even try, play. And basically what you have is you have all the character names in the play up down both axes. If they appear in the same chapter or scene, you have a color, and the color is linked to the frequency, so the very dark cells are the most frequent. So that looks like an image. Why not put that directly through an existing structure? Wouldn't that be great to be able to use existing neural network architectures, for example, that we've already trained on images, and actually push entire adjacency matrices through in order to classify graphs, in order to transform graphs? It turns out you can do that, and people have, but the results aren't great. And some of the reasons why is adjacency matrices have some issues, and that if we just permute the order rows, they characteristically change significantly. Also, they get as big as the graph, and the spatial organization in any of these situations do not relate in any way to the organization of the data in the network. And we're in an image, we're used to things having neighborhoods and things being close to each other if they are next to each other in an image. And they're sparse, so it's quite wasteful to do this because the matrices are huge. So we come back to this concept of an embedding. What we need to do is take our adjacency matrix and capture a lower dimensional form. So we have a graph on the left and an embedding on the right. So this is coming back to dimensionality reduction as we did before. And what we want to do is be able to take that graph and project it into a vector space of lower dimensions so that the layout of properties in that space still bears some resemblance to the network patterns in the graph. And it turns out there's a huge body of mathematics on this, which is graph spectral theory. And you can take a graph matrix A, and by computing its Laplacian, actually calculate something called a spectrum. But essentially, all you're doing is PCA on the Laplacian matrix, which is an interesting parallel with the first zero-order dimensionality reduction technique. And then the eigenvector matrix actually completely represents the graph again, but now you have a set of eigenvalues telling you how important the information in each eigenvector is, and you can decide to take a subset and reduce your dimensional space, and then use this as input to a neural network. And people are doing that with some success. They're showing that this is outperforming specialized techniques that process on graphs. And an interesting thing here is we can decide to take columns in order to decide how big our embedding should be. But the rows actually relate to individual nodes in the graph again, just in the new embedding space. So a couple of papers to follow on that further is that these two sets of researchers did exactly that. The spectrum-based neural networks for fraud detection. They took in graphs, they took subgraphs, and they went through the spectral theory to compute graph spectrum. And then they started taking node information and projecting it into the spectral space to build up these feature vectors that completely represented the graph, and used that in fraud classification. And the similar technique, the second paper actually set out to show what could be done with conventional convolutional neural networks for images, again pushing through these processed adjacency matrices. So that's a bit of a progression from lots of manual feature engineering to get the information out of the graph to finding a representation that embodies the graph and pushing that through a network that can then do the mapping for you. The third very interesting area that builds on that again is semi-supervised learning with graphs. I'm going to talk a little bit about semi-supervised learning to start with. So basically with supervised learning, we have a training set that includes our input vector, our features, and our expected sample labels for our classes. And we'll use something like a neural network or something to produce outputs, and we'll train based on the error between the expected output and our input and our actual output and our expected input. And we'll do that to train the network. The issue is actually having labeled data is difficult to find and it's expensive to acquire. So what do you do when you only have a lot of data but maybe you've only got 10% of it labeled? The temptation is to throw away 90% of your data and only use the 10% labeled. This limits the training data set sizes. It means you can't use larger neural networks because you don't have enough data to train it. And it might even force you away from supervised techniques. So semi-supervised learning is a complete an approach specifically to deal with this. Now let me just give you an example. Say we have a data set with 1,000 samples, 10% of which are labeled, whether they're two classes. And let's say there's the labeled data on the side, so we can see the instances there. And we might draw a decision boundary at a particular point in that graph in order to classify between those two. Now, if we could only understand what the true underlying distributions are, which are the sort of bell curves that we don't actually know, we don't have them labeled, but if we understood what those were, we would put a completely different decision boundary on our data. So the idea is, with semi-supervised learning, is to find ways to pull in the unlabeled data and use it to bolster the classification that we're doing. This is the same example, but in 2 dimensions. So if you only train the classifier on the subset of the data, you would decide on a decision boundary like that, where the whole underlying data set, which is in grey, I know I put squares and circles, but we don't know that that's the case. But just to illustrate, imagine that's the true distribution shown in grey. Our decision boundary would be very different. And this problem exacerbates as we go up dimensions, that without building in the priors, if you like, from the unlabeled data, you lose the ability to properly form decision boundaries. So the way that people do this is quite simplistic to start with. It's split the problem. You've now got 2 machine learning problems instead of 1, or 2 prediction problems instead of 1. And this is sort of described by sort of transductive and inductive learning, in that one problem is to learn the labels for our unlabeled examples, and so flesh out our training set. That's one problem. And then the other problem is actually to build a predictor that can handle and generalize to any input that we haven't been seen. So and if we regard those as 2 separate problems, we can actually use 2 separate techniques to tackle them, and then combine them within the whole system. So semi-supervised learning is not new. There's lots of different approaches, and the simplistic way is to introduce smoothness and regularize over the data set. If somehow you could cluster and just use k-means to see if there are any clusters in the data, and then propagate labels out from that. The same with manifolds, do they lie on the same surfaces? But graph-based relationships are particularly powerful, especially if you already have data, which is graph. You already have potentially reliable set of proxies in order to start inferring your labels. But it basically all boils down to using some method of inference, which you can have confidence in, to label the training data set. So approach 1 is to split the problem. So imagine if we have a 2D, there's no axis, but imagine we have a 2D feature space, a whole bunch of points, only 2 of which are labeled. Then a very straightforward approach is to use k nearest neighbors to propagate the labels across the distribution, like so. And k nearest neighbors, you're actually building a graph behind the scenes. If you don't often visualize it like that, but you're building a graph of connected components behind the scene, and then you can use that neighborhood graph to then fully label the data set and use that to train a larger classifier that would do a better job of generalizing for input that you haven't seen yet. So that was an example of using an algorithm to impose a graph on your data, And there's plenty of examples out there of people building, using facial recognition and facial similarity to build facial graphs over images, and then using that as a proxy for some other, for some further classification. But of course, if you've got a graph, you've already got rich relationships, and often multiple ones, that you can use. So you could use the contacted graph, for example, and look at the frequency of contacts between different entities in that graph and decide, based on that, how far to propagate labels out in order to increase the size of your training data set. So graph data automatically gives you that approach. A further evolution of that, and the last thing I'm going to talk about, is something that I'm working with now, which is graph-based convolutional networks. And what this does is, instead of trying to split the problem into let's propagate labels for our data set and then use graphs, propagate data for our data set using a graph, and then classify, what people are doing, and they're actually starting to change the nature of the kernels within convolutional neural networks to actually implicitly process on graphs. So this is an excellent example, and this guy's source code up here, from the University of Amsterdam, and it runs in TensorFlow. And essentially what it's doing is you feed it adjacency matrices, and then each node in the network is actually computing the spectral graph, and then they've actually redefined convolution on the graph based on spectral theory. So there's no longer convolutional neural networks, deep neural networks, essentially doing convolutions between the inputs and the weights by multiplying the input vector with the weights and summing that up. What this is doing now is doing graph-based convolution at each point within the network. So this means these neural networks are starting to take graph representations and be able to produce graphs. And the interesting thing is, in that process, it can take partially labeled nodes and will propagate nodes out across the network in the result automatically. So it's like the semi-supervised learning is actually built in, which is quite remarkable. The downsides with these is a normal neuron in a neural network will basically take an inner product between two vectors and sum them up. So n multiplications and n summations. This needs to do an eigenanalysis and a Fourier transform on every node. So the computational cost is significantly beyond using a traditional architecture. But it does have some benefits and some, because we can produce graph outputs, some better, some further potential applications, because you can do things like produce a different, you can transform graphs, etc., through the network, and do things like link prediction or graph simplification. So I recommend checking out the code on that. The semi-supervised learning you can address, so to summarize, semi-supervised learning addresses a huge problem, which is lack of labels in supervised learning. And it can improve training accuracy just because you're bringing in more information from unlabeled data. And because you have more data to train with, you can build bigger models. And graph representations are a uniquely powerful way to do it, especially if you already have graph data, because that gives you these additional proxies. As a takeaway, so with some of the people that we work with, the graph data sets represent some hugely rich sources of information. When people are parsing these data sets manually and able to see what they do with a graph database, they're often amazed at the way they can slice their own data sets and information. So machine learning, applying machine learning there to drive exploitation of that and to automate some of this manual process is very important. And we can start using information from graph data sets immediately today, either by drawing analytics or by pushing them through traditional architectures. And just to reinforce the point of semi-supervised learning, graphs are a uniquely powerful way to do inference across the data set. Okay, and new powerful graph-based architectures are emerging. That's everything. Thank you. I hope that was useful.